All right. Okay, so this is our first lecture back after the term test. So we will pick up, sorry, I need to close that. Okay. So we will pick up where we left off on Tuesday last week, which was discussing logistic regression. So this is lecture set number 5. So I would suspect that we'll finish lecture set 5 today, and we'll move into lecture set number 6, which is also on logistic regression, but it's a discussion on model evaluation, model comparison via techniques like prediction, residual analysis, and all this sort of thing. Lecture set number 5 was meant to just kind of illustrate the formulation of different types of binomial GLMs, with the most common one being the logistic regression model. Oh, sorry. I need to okay. So as a reminder, we have basically like the goal of binomial regression, I guess you can call it, like in the general sense, is to model the probability of observing some event. Now, with that being said, the response variable is still a count of the number of successes, and it can be between 0 and n for each observation, or it can be between 0 and 1. So in the situation where each observation only has a sample size of 1. So these models can be used to model the probability of some event in either the binomial or Bernoulli case, because the Bernoulli is a special type of binomial where n is equal to 1. So these are going to translate to both situations and be used in the same way. The example that we're going to look at in lab is based off of a situation where we have a binomial response. Or sorry, the example we're going to look at in lecture is based off the situation where we have a binomial response. So we will look at different examples of this type of outcome. We'll actually see a mix of binomial and Bernoulli in lecture set number 6 when we look at the senility data, senility data. But anyways, until then, the purpose of lecture set 5 again is just to introduce the binomial generalized linear modeling scheme. So again, we're interested in modeling the probability of some event. There's 3 common types of binomial GLMs. There's what is called the probit model. In this situation, our tolerance function is the CDF for a normal distribution. There is the logistic model. In this situation, our CDF or the tolerance function is written on slide 9. So this is where we model the logit, which is the log odds of the event. And this is the most common type of binomial GLM. So this is the GLM that you will see, or that fits by default in most software packages. So we're going to spend a bit of time in this lecture setting this up so that we understand how it works. And that'll help us to kind of move into building interpretations of the other models. One of the key reasons I think that the logistic model is so popular is because it actually has a direct interpretation that's understandable. Whereas with the probit and the complementary log-log model, which is the binomial GLM where we use the extreme value tolerance distribution, you can't get the same direct interpretation from the fitted model. But this idea, I think, will make more sense to us momentarily when we start looking at the example of interest. Okay, so to illustrate the logistic regression model, we're going to use this Beetles data. And this is going to be a data set we use throughout lecture set 5 and 6. In lecture set 6, I bring back some of the key points just so that we have them directly available to us. But this is our sort of illustrative data set. This is what would be considered kind of like a simple regression data set because we only have one explanatory variable and we have one response variable. So with this data set, X is going to be dosage level. So we're measuring at each dosage level, we have little mi or little ni beetles being exposed to to gaseous carbon disulfide. And we're counting the number of beetles that die, unfortunately, as a result of this exposure. So this is a binomial situation where yi is the count of the number of deaths, and then n or mi minus yi in this case would be the count of number of beetles that survived. So we have a binary outcome, death, not death, and we have a set number of trials at each exposure level, and then we have a count of the number of outcomes, right? So this is clearly a binomial. Each observation is clearly binomially distributed with set number of trials and set number of and found number of successes. So what we're trying to do here is model the probability of death based off of the exposure level. But again, the response variable is the count, which is the binomial random variable. All right. So on slide 12, we have a scatter plot that's showing the proportion of beetles killed. So this is going to be yi over mi, so the observed values, against the dosage, the log of the dosage level, which is given in the previous table. Okay, so you can see that we sort of have this kind of like S-like shape, or inverted S-like. Well, no, it's like an S-like shape that that shows the relationship between the proportion killed and the dosage level. It would make sense that we have this kind of S-like shape because we're modeling a probability. So we know that the probability has to be constrained between 0 and 1. So this would be, more kind of what you would expect to see in contrast to the linear relationship that would imply you can go outside those 0 to 1 ranges, which again wouldn't make sense because we're modeling a probability. And what we are going to do here is use a GLM. So we are going to use, we're going to establish a link of the response variable, so the mean of the response variable for each observation, and then link that to a set, to a linear model. And that link function is going to allow us to accommodate for that shape. All right, so we're going to use the logistic regression model. So we are mainly focused on introducing this model. Again, very popular type of model, mainly because we have we can directly interpret the model parameters to understand how the response variable is changing with the explanatory variable. The logistic regression model says that the logit of pi is equal to beta 0 plus beta 1x. The logit is the same thing as the log odds. Okay, so this thing here, this whole function is the log odds. All right, so we'll spend a bit of time talking about interpretation in a little bit. We'll go over the definition of the odds so that everyone understands it, but you can see from the formulation that it's basically a ratio of the probability of observing the event divided by the probability of not observing that event. Okay, and then we can say, since the logit is equal to the following, the probability of observing the event at iterate, or for the ith observation, is going to be given by the following. This is just the inverse of the logit. And this can be computed directly in R using the ilogit function, for example. We'll talk about that in lab tomorrow. So the point is that from this model, we can interpret the results in terms of the log odds, or in terms of the odds, which is going to have more meaning than the log odds. And we can also get direct estimates of the probability of success. We can do this with the other binomial GLMs as well. Getting direct estimates of the probability of success is quite easy because you just have to invert the associated link function. So for example, with the probit model, you just have to invert the CDF of the normal. And all these things can be done directly in R, and we're going to go through examples of that tomorrow. We're really just focused on interpretation today, but just to give you an idea of what kind of output you can get from these models and how using statistical software, it's quite easy to get direct estimates of that probability of success. Okay, so we specified the model, which is that logit model given on the previous slide. We're just going to quickly highlight the steps of the model fitting process here, just for illustration purposes. But this is going to be the last bit of really like formal mathematics we're going to see for a little while. So when we fit the logistic regression model, we do this through maximum likelihood estimation. We're not going to have closed form solutions, so we're going to end up with an iterative weighted least squares which is a iterative weighted least squares algorithm to fit the model, which again is basically like a Newton-Raphson style algorithm for GLMs. Okay, so the first thing is for the logistic regression model, we're trying to maximize the likelihood with respect to beta 0 and beta 1. So we can write here that L of beta 0, beta 1, given X and Y is equal to the sum from I equals 1 to N of YI beta 0 plus beta 1 XI minus NI log 1 plus EXP beta 0 beta 1 X plus log NI Y. And then just for clarity, NI is equal to MI. Using interchangeably. Not sure if that's a word, but basically I'm switching between them, but they're the same thing. So MI or little NI in the context of the example, they're both just counts of the number of Beetles at each of the dosage levels. All right, so our goal is to optimize this likelihood function or log likelihood function in terms of beta 0 and beta 1. So we're going to do this by finding the score functions for each. Okay, so we can say S beta 0 is going to be DL by D beta 0. This is going to be the sum from I equals 1 to N of YI minus NI EXP beta 0 beta 1 XI divided by 1 plus EXP beta 0 plus beta 1 XI. Okay. Which is equivalent to the sum from I equals 1 to N of YI minus NI II. Right, and then we have S beta 1 is equal to DL by D beta 1 which is going to be the sum I equals 1 to n of yi xi minus ni xi exp beta 0 plus beta 1 xi 1 plus exp beta 0 plus beta 1 xi, which is equivalent to the sum I equals 1 to n of xi yi minus ni pi. Okay. So you can see it's actually pretty straightforward to evaluate the score functions, but obviously solving for beta 0 and beta 1 directly is going to be impossible. So we have to use an iterative procedure to find the MLEs. Okay. So given our score functions, the next thing that we need to do are find the information functions. And then once we have the information matrix, we can put our iterative weighted least square algorithm together using the general expression that we established back in lecture set number 4, I believe. Okay, let's make sure. Just give it another second in case anyone is still copying here. Right. So the next thing we can do is show the formulation of the information matrix. Now, just for clarity here, the way that this works is we would have the following. So you would have d L squared by d beta 0 squared, d L squared by d beta 1 squared, or sorry, d squared beta 1, right? I don't remember the exact. D squared L. And then on the off diagonals, you have the partials with, or the double derivative with respect to each parameter. Yeah. Oh, d by d. Okay, so that's how the information matrix will be computed in the bivariate case. And then you can imagine as we extend to more dimensions, the partial derivatives that you have to consider become more complicated. But this in the bivariate case is the structure of the matrix. So you can we can show fairly directly, given the simplified expressions from the previous slide, that this is going to be ni pi I 1 minus pi I, the sum I equals 1 to n, ni xi 1 minus pi I. the sum I equals 1 to n xi pi I 1 minus pi I, the sum equals 1 to n ni xi squared pi I. All right. And then, given the equations for the score functions and the information matrix, now we can update our parameter estimates using the values given below, where u is beta 0, beta 1, beta. Sorry, beta is beta 0, beta 1. U is the score. Right. The off diagonals. Oh. They should be. There's missing a pi. Okay, so from that, it should be pretty clear like how the process is going to evolve. We've looked at examples of this already. We actually have one on the second assignment, and we looked at one in the Poisson case back in lecture set number 4. We went through an example of that in R. We'll go through an example of this tomorrow in R as well, just for illustrative purposes. But I think, hopefully it's clear like what is going to happen here. We're going to set an initial value for beta 0, beta 1. We're going to evaluate the score functions, and we're going to evaluate the information matrix at beta 0, beta 1. We'll get an update for beta 0, beta 1, and then we'll reevaluate the score and information at that update, and we'll just iterate until we reach convergence. Under that process, so if we start from beta 0, beta 1 equal to 0, we arrive at the following model. So we have the logit of pi I is equal to negative 60.717 plus 34.270 xi, right? So this will be done in the way that we just described, and actually we can do this directly in R. We'll see examples of that tomorrow as well. At convergence, we have a log likelihood value of negative 186.235. Note that this is an approximation to the MLE, right? So this is given approximates of the MLEs. So it is the largest or close to largest value. That's important because we're going to talk about model selection criteria a little bit later on. So when we are using our model selection criteria, specifically those that are based off of log likelihood values, you need to know if you are maximizing or minimizing the likelihood. Now we're using MLE, so we're maximizing the likelihood, but technically it's a it's a monotonic function, and there are algorithms where you might minimize the likelihood rather than maximize it. And it's the same thing. It's just the difference of a negative out front of the expression. But in this case, we're finding the maximum, right? So right now we're sitting at the top of what is hopefully the largest hill on the likelihood surface. So when we go to evaluate the models based off of different selection criteria, we have to remember that we're penalizing the largest value. This is going to be important, as you will see in a little bit later on. Okay, so we have beta 0 and beta 1 at convergence. We have our log likelihood value based off the MLEs of these values at convergence. And then we have our deviance, which we talked about before. We're going to go through an example of using this again momentarily. We have our information matrix, and then we have the inverse of the information matrix. So there's a lot of different things that we can pull out from this output. Here's the fitted model. Okay, so this is sort of a cheeky expression of the fitted model. What I did here is I just plugged in X into the model. I computed pi hat, and then I just put a straight line type model through it. We'll look at how we can smooth this out tomorrow so we can get a really good approximation of the fit. But this is just the fitted model based off of the 8 observations that are available to us. So, and again, this model is showing the estimates of the proportion of beetles that would die at each dosage level. Okay. Any questions? Okay. So we're going to talk about 2 things. We're going to talk about model evaluation based off of what has been outputted, and we're going to talk about interpretation and utilization of the model based off what has been outputted. I think that the natural place to start is with using the model. All right, so let's consider for example, one of the dosage levels in the experiment. Okay. So we have is the logit of pi I hat is equal to negative 60.72 plus 34.270. Okay. All right, so let's say, suppose xi is equal to, I don't know, let's pick a dosage level somewhere in the middle. So maybe we'll go with 1.8, okay? Suppose xi is equal to 1.8, then the logit of pi I hat is equal to negative 60.717 plus 3 plus 34.270 times 1.8. Right, so in terms of usage, it's actually incredibly similar to what we would have had with a regular linear model, right? So we're really just plugging into the value directly or into the model directly. So this is going to give us 0.969. Okay, so the 0.969 is an estimate of the logit of the probability of death at this dosage level. Okay, so this 0.969 so therefore, the first thing we can do is kind of like unpack it. So the logit is the log odds. So the estimate of the logit of probability of death, which is estimate of log odds of probability of death. Okay, so the most natural thing to do to unpack this first value is to take the exponent of that value. So we have log odds. So the log of pi I hat over 1 minus pi I hat is equal to 0.969. Okay, so therefore, pi I hat over 1 minus pi I hat is equal to exp 0.969. Which is equal to 2.635. Okay. So now what we have are the odds of death at this, the odds that a beetle dies at this dosage level. So this is a ratio of the probability of death to the probability of survival. Okay, so this is basically telling us that the probability of death is larger than the probability of survival at this dosage level. Okay, and it's larger by 2 point. I have to be careful with that interpretation, but this is telling us compared to the probability of survival, right? Okay, so interpreting the odds is a is usually done sort of in a 3-to-1, 1-to-3 style manner. Let me see if I can get a direct interpretation. I think we can say 2.63-to-1. whatever, it doesn't matter. Okay, so this would imply, so since the odds, the odd is greater than 1, this is telling us the probability of success, or the probability that a beetle dies at this dosage level, is greater than the probability it survives. Okay, so we now have we basically know that at this particular dosage level, there's a larger chance that the beetle is going to die than they are going to survive. So we can also convert the odd into a probability, right? And this can be done directly from the beginning via the logit function, but it can also be done simply by rearranging this expression and solving for pi. So if we were to do that, we should end up with 0.723. So we would have it follows that it's equal to 0.725. So therefore, the estimated probability of death at 1.8 well, log based, I'll just write at xi equals 1.8. Is 72.5%. Okay. So we can get a pretty nice interpretation of the result based off of this particular model. And we can actually get a couple of different things out of it, because we can get an expression for the log odds, which is what we find directly. Then we can compute the odds. So in some situations, we might want the odds directly depending on the application. Maybe if it's like, for example, something related to gambling or betting, typically in that area, odds are used to express the outcomes of the particular event. Or if we want, we can directly get the probability, which, I mean, personally, I find a little bit easier to interpret and understand, probably just because of how often I work with probabilities and how little I work with odds. But they're easy to find from one another, which is the main takeaway. So if you have the odds, you can easily find the probability. Okay, so that was the first thing I want to talk about. So this is just directly inputting a value into the model and what you get out as a result of that. Now, the second thing is actually interpreting the model parameters. All right, so in this particular illustration, interpreting the model parameters isn't overly useful because of the scale at which the dosages are sitting on and how we would directly interpret the values. But just for illustrative sake, we'll look at the general interpretation, and then we'll try and bring it back into the context of the problem. Okay, so just like with an SLR model, what we're going to do is basically interpret the y-intercept and interpret the slope, if you will. Now, in this case, both values represent log odds again. Okay, so when x equals 0, the log of pi I hat over 1 minus pi I hat is equal to negative 60.717. Okay, so this means that pi I hat over 1 minus pi I hat is equal to see it, you're going to notice here, like these are massive numbers, right? But this is basically saying like when there's no dosage, okay, the odds are going to be, the odds of death are 4.275 times 10 to the negative 27, which is basically saying like if you don't expose them to any carbon disulfide, the probability they die is 0, which makes sense, right? Like you wouldn't expect there to be a probability of death associated with 0 dosage. And then at the same time, if we compute the probability here, we should observe a similar idea. Right? Which is the same result. Okay, and this is also equal to pi. Okay. So basically, when x equals 0, the probability of death is effectively 0. Right? Sorry, and this would be for beta 0. If we consider beta 1, what is this telling us? This is saying as x, or as the dosage level increases by 1 unit, the log odds increase by 34.270. Okay. So therefore, the odds of death increase by exp to 34.270, which is equal to right, so this is going to be massive, 7.643 times 10 to the 14, and pi I hat increases by 1. Right? So basically what we're finding here is, in terms of the general interpretation of the model, what the model is telling us is as we move the dosage level by 1 full unit, the probability of death is essentially increasing by 100%. And this seems a little bit insane when you think about the interpretation. Like, so you're telling me as I move across 1 unit, I'm getting a 100% increase in the probability of death. But if we go back and actually look at the scatter plot, so you can see that we're measuring this on a scale of about 0.01 units. But if we move from say 1.7 to 1.8, you can see that the observed probability goes from about 0.05 all the way up to about 0.85. And if we look at the table of counts, you can see, so for example, if we look at 1.7, the number killed is 6 out of 59. If we move to about 1.8, we're now at 52 out of 63. So the model is basically reflecting that a full unit increase in the dosage level is going to drastically increase, or that the probability of death is going to basically be certain given that overall increase. Now, given that 1 unit increase. Now, again, I can appreciate that this feels a little bit extreme. So what we could do is try and simplify our expression by looking at it on a more reasonable scale. So for example, one of the things that we can do here is, so I'll just kind of carry this over. Okay, so consider a smaller change in x, say x to x plus 0.01 for. Okay. So if we were to consider the two models, we would have logit pi I is equal to negative 60.717 plus 34.270 xi. And we would have logit pi I is equal to negative 60.717. I'll call this 1. I don't want you to think I'll call this logit pi I1, logit pi I2, plus 34.270 xi plus 0.01. Okay. So the change between, or rather, okay, so therefore, logit pi I2 minus logit pi I1 is equal to, so if we subtract the two models from each other, the intercept terms fall off, and we basically just end up with 34.270 times 0.01, which is 0.34270. Okay, so this is telling us that the change in the log odds when we consider a 0.01 unit increase in the dosage is going to be 0.3427, right? So as x increases by 0.01, the log of pi I over 1 minus pi I increases by 0.34270. Okay, so this corresponds to pi I over 1 minus pi I increasing by 1.48, 1.408746, and pi I hat increasing by and it's still very high, 0.803, right? So this is now telling us, like, basically as we change the dosage level by 0.01, the probability of death is going to increase by almost 80%, right? So for each 0.01 unit increase, we have an 80% increase in the probability that one of the beetles dies, which is still very large. And it's basically, it's what it's showing us is that the carbon disulfide is extremely toxic in this case, or that carbon disulfide is extremely toxic to these beetles. Okay, so any questions? So quite a bit to unpack there, but I think that it's valuable to go through the process because from the logistic regression model, again, I talked about how this is the most popular model, and you can see that one of the reasons why this would be popular is because you can get the odds and you can get a probability out of it, and the interpretation and unpacking of those values is pretty straightforward. You can also get the probabilities from the other two models. You just have to invert by the appropriate function. We'll look at examples of that in R tomorrow in lab. And then the interpretations have a little bit less meaning, because now, like you're talking about, you can still interpret the parameters in terms of the probabilities, but the direct interpretation of the parameters isn't as valuable, because you're not talking about a change in the odds. You're talking about the change in, well, you can't get a reflection on the odds, for example. You would have, it's a function of the normal distribution. So you just, that particular component of it breaks down. But getting the probabilities out is still quite straightforward. So, okay, evaluation. So I just want to go through our deviance test again here. All right, so we have step 1, H0 fitted model is sufficient versus HA maximal model is required. Okay, on step 2, we have alpha equals 0.05. All right, on step 3, we have D equals 11.23. Right. Okay, so I'll just give you a couple of values based off of this. So first off, D is distributed chi-square n minus p. Okay, so this is going to be distributed chi-square 8 minus 2. Okay, so this is chi-square on, or sorry, these would be equal signs. Okay, so this is distributed chi-square on 6th degree of freedom. All right, so a chi-square on 6th degree of freedom at 0.05 is equal to 12.59, I believe. Oh yeah, there we go. Good memory. Toot my own horn, I guess. And then the p-value for this test would be 0.0815. You can actually see we're getting pretty close to rejecting here. So there is some suggestion that this isn't the best fitting model. We'll talk more about what we can take from the deviance measure directly, but in general, what we're trying to find with the deviance is, one, like evidence against the null, but you also want the deviance value to be close to the expected value of the chi-square, which is the DF. Okay, so in this situation, we can reject, so we have evidence that this model is sufficient. However, we're getting very close to the border. So we'll talk more about how we can use the deviance a bit later on, and what this would mean in terms of model comparison, because all these values are really most beneficial when we're comparing different models on the same data set. But in this situation, we can reject, or we don't reject the null, so we have evidence that the model is sufficient. So Okay, so there's not enough evidence to suggest that the maximal model is required. So we do not have to reject the null here. But again, that deviance measure is quite large compared to the df of the chi-square distribution. And that does have meaning to us in terms of how we would evaluate the fit of the model. So while at the 5% significance level, there is evidence that this model is sufficient compared to the maximal model, the fact that that deviance value is so large compared to the degree of freedom, it's almost twice the size, would indicate that there could be a problem with the model fit. And we'll come back in lecture set 6 to discuss how we would define that problem and what we can do about it. And again, we'll also discuss how we can use deviance values from different models fitted to the same data set to pick which model is better fitting compared to another, as most of these values really have the meaning of these values is really best within the context of a comparison. All right. Any questions? One other thing I would recommend too, just based off of the interpretations that we discussed here, it's worth looking up how to distinguish between the odds and a probability and the relationship between the two. So, for example, this here is saying that there's like a 2.653 to 1 odd of 2.653 to 1, or the odds are 2.653 to 1 in terms of death. Okay, so that's like saying across a set number of trials, you would expect 2.653 deaths to every 1 survival, essentially. And then you can also see like how this relates to the probability and how one is computed from the other. It's not an overly taxing calculation, but it is helpful to have an understanding of what the odds mean. But basically, like when you're writing something as this to this, when it's like 3 to 1, that means the probability of success is higher. And when it's 1 to 3, that would mean the probability of failure is higher, essentially. And you can compute exactly what that means in terms of the probability. Works out to being a quarter success rate. But yeah, it's helpful to review these just to have an understanding of the relationship between the two, especially as we study logistic regression. Okay, so we talked about interpretation. We went over the model fitting steps. We talked about evaluation. This is our second example of evaluating a model based off of deviance. Okay, so we saw the same example in lecture set 4, when we looked at inference directly, and we did an example in the context of a Poisson model. All right, so we're going to go through the model fitting process in R tomorrow. It's very straightforward. It's just the GLM function. You'll actually see all of the output we discussed today within that function. There's one other thing I wanted to mention here before we move on. So this reminds me of one other thing I almost forgot about. So we have our deviance measure, and we can also do inference about model parameters. Okay, so remember that the model parameters in a GLM are normally distributed. So we can actually conduct inference about those parameters using the standard normal distribution. Okay. So for example, let's look at beta 1. The idea for beta 0 would be very similar, but we'll just do it in the context of beta 1. Okay, so for beta 1, we had beta 1 hat is equal to 34.270. And then we can get the standard error of beta 1 hat. So this is going to be the square root of the information function to 2, right? So you'll remember that the information function, the inverse of the information function in the diagonal slot that corresponds to B1. So the information matrix that we computed and shown on slide 16, this here is the variance of beta 0 hat. This here is the variance or the estimate of the variance of beta 1 hat. And then these two things are going to be the covariances, right? So this is going to be the covariance beta 0, beta 1. So from the variance, we can directly get an estimate of the standard error. So the information matrix at 2, 2, so the second row, second column, that is an estimate of the variance of beta 1 hat. We take the square root of that, we have the standard error. So in doing that, we can build a confidence interval. So beta 1 hat plus or minus 1.96 multiplied by the standard error of beta 1 hat. Okay, so this is going to give us, the square root of this value here is going to be 2.91. Right, so that's the square root of 8.4779. Right, so that's 2.91. So then we can easily build a confidence interval based off of this value. So we have 34.270 minus 0.96 times 2.91. So that gives us 28.5664 to 39.9736, right? Okay, so what this is showing us is, first of all, in terms of significance, it's telling us that beta 1 is certainly different from 0. So there is most certainly a relationship between the logit of pi I and the dosage, right? So since interval does not right? So there's a linear relationship between the logit and the value and the dosage level. So what we can also do here is actually determine like how the odds are affected by beta 1. And it's a very similar idea. So if we take the exponent of the bounds, right, we're going to get massive numbers, obviously. So since E 28 0.5664 to E 39.9736 does not include 1, that gives evidence that pi I is greater than 1 minus pi I as dosage increases by 1 unit. I apologize for cramming everything together. I didn't think I would need multiple slides per each of those explanations. But basically what I'm trying to get at here is, given the information matrix and the estimate of the slope, we can construct a confidence interval using the standard normal distribution, right? So this here is just a 95% CI. And this confidence interval, first of all, you can see that the bounds on the interval are much greater than 0, right? Like 0 is nowhere close to being inside this interval, which means that there's a linear relationship between dosage and the log odds, right? This is to be expected. But what we can also say, because we can directly interpret the odds, and we know that the odds are a ratio of probability of success to probability of failure. So if we transform the confidence interval to be in terms of the odds, and that can be done just by exponentiating each of the bounds, if that interval was to contain 1, that would indicate evidence that the probability of failure and the probability of success does not change as X increases by 1 unit. But in this situation, it's very clear that 1 is nowhere close to being inside this interval. Like, we're talking about 2 values that are on the scale of e to the 17 or something like this. But had it included 1, then we would have evidence to suggest that the odds of, or that the probability of success is the same as the probability of failure as we increase by 1 full unit. All right, any questions? Okay, so in this lecture set, we introduced the binomial GLM, the general framework or idea behind why you would fit a binomial GLM. We talked about different types of link functions, which are based off of different types of tolerance distributions. The idea there is that if we don't consider a transformation of the response, we're going to end up getting models where the probability is outside of a range 0, 1, which is impossible based off the definition of a probability. There are 3 common types of link functions. The link function that would lead to the logit model. Well, actually, no, let's say the link function is the logit. The cumulative distribution of the PDF, which leads to the probit model, and then the extreme value distribution, which leads to what is called the complementary log-log model. And those are the 3 common types of binomial GLMs, all of which can be easily fitted in R, but the default model is the logistic regression model, which I think is mainly based off of interpretability of the model. So again, you can get direct interpretation of the odds quite direct, in a very straightforward manner. But you can also unpack the probability of success with that model and the other 2 models in a pretty straightforward manner, especially considering the access to software that we have. Some of the other nice things about the logit model are, for example, when you conduct inference about the parameters, you can phrase them in terms of the odds, which has meaning to us, because if that interval was to contain 1, that would imply that the probability of success and failure is not changing as x increases by 1. So there's some nice inferential characteristics that you can kind of pop out of this model. But again, we could also put these on the probability scale and directly discuss the probability change as x increases by a unit, which can also be done with the other models as well. So what we're going to do in the next lecture set is discuss evaluation and discuss comparison. So we're going to look at a variety of different techniques to discuss or to evaluate the model. So we're going to talk about goodness of fit statistics. We've already seen one of these, which is the deviance. We're going to talk about R-squared type measures. So values that are meant to reflect or values that are a ratio that are constrained between 0 and 1, that are meant to basically illustrate how much information is gained by a particular model with reference to another model. We're going to talk about likelihood-based measures, so values that are constructed directly from the likelihood at convergence. We'll look at residual analysis, though in the case of GLMs, residual analysis isn't always meaningful. It really depends on sample size and how much information you've collected at each of the observations, at least in terms of the binomial model. We'll talk about over dispersion and under dispersion. So I mentioned before that the deviance is a value that can be used to conduct a hypothesis test about the suitability of the fitted model versus the maximal model. But we can also use the deviance to determine if there is evidence that the variance of the response variable is larger or smaller than it is expected to be under the binomial assumption. Okay, and we'll talk about methods for dealing with this. And then we'll discuss how we can use all of these statistics, the residuals aside, to compare the different binomial GLMs on the same data set and what we can take away from a comparison of those values. All right, I think given that I only have 5 minutes left, I'll just stop here for today because it makes more sense to kind of be able to get into this and keep moving forward rather than break it up into different sections. So I'll stop here for today. I apologize for being a little bit early. And we'll have lab tomorrow where we will basically go over concepts that we discussed in lecture set number 5. So model fitting, interpretation. We'll look at superimposition of the curves onto the plot and that sort of thing. On Thursday, we'll get into lecture set number 6 and maybe move into lecture set 7, where we discuss some offshoots of other types of binomial GLM. So for example, what you do if you have ordinal responses, nominal responses, multinomial responses. And then next week in lab, we'll basically discuss implementation of those and probably move into the Poisson distribution, I would imagine. I think you also have an assignment due Friday, which is the second assignment. So that is on work before lecture set number 5. And then I'll post assignment number 3. And next week, actually, I think is our last week before we enter the reading break as well. And when we return, we will have another term test coming up shortly. All of those details, though, are given in the course outline. Okay, so I'll stop there. If anyone has any questions, I'll hang around. And otherwise, I will chat with you guys tomorrow.